All right, hello. Today we're working through a problem from a robotics course that I'm doing at uni. And in this problem, we've got a camera mounted on a robot. We know where this camera is relative to our world frame, and we want to work out all of the various matrix parameters that we need to be able to take some sort of object in the world frame. If we know its x, y, z coordinates, we want to be able to calculate where exactly that's going to end up on the camera's image, like which pixel it's going to show up on. So I'm not going to spend a huge amount of time on the underlying theory. The point here is just to sort of do a bit of a walkthrough of like how we kind of answer a question like this. But I will sort of cover the basics just so that we can kind of know which equations to use and that sort of thing. All right, so we're starting off with some of the camera parameters. We know that the field of view of the camera is 80 degrees in the x direction. It's 50 degrees in the y direction. And we know that the camera has 1280 by 720 pixels. I don't know if any cameras actually have those kind of parameters. I just made those up. So then we've got a sort of diagram of where the camera sits relative to the world frame. So we can see that the camera is sort of offset from the world's origin point a little bit. We've got a handy translation vector that tells us how to get to the camera from the world origin. So we'll be using that later for sure. And then if we look at some of the axes that have been drawn around the camera here, we can see that the camera's frame is not exactly the same as the world's frame in terms of what is considered X, Y, and Z. So we'll take that into account as well. And then finally, we've got a note saying that there's no offset between the lens's optical axis and the center of the image sensor. So we'll dig into that a little bit too. What we want to find out is the intrinsic camera matrix K. We also want to find out the rotation matrix of the extrinsic parameters. So this is basically just saying what is the rotation of the camera relative to the world frame. We usually call that R, shockingly. And then there's also the translation vector from the world frame to the camera frame. That is called T, shockingly, although sometimes it's denoted as C, T, C, W. This is a sort of indication that it's a transformation from the camera frame to the world frame. All right, so I'm going to start with the intrinsic camera matrix K for no particular reason, really. This is where I'm going to start. So before we begin with that, we need to talk about what this note here means. So no offset between the lens's optical axis and the center of the image sensor. So what that means, if we start working on the intrinsic parameters, is we've got a lens, and then you've got the world out here with a tree or something in it. And this lens has an optical axis, which is basically just the line that runs straight through the middle of the lens, perpendicular to the sort of plane of the lens. And what this little note here is telling us is the lens's optical axis, which we've just drawn before, and the center of the image sensor do not have an offset. So that means that if we sort of imagine our image sensor here, that it is going to sit, or I'm not sure if I'm drawing that right, sort of do it intuitively. The image sensor is going to sort of exactly be positioned in such a way that the optical axis goes straight to the middle of the image sensor. I don't know if I drew it correctly there, but hopefully you get the idea. The distance from where the optical axis intercepts the image sensor, that distance there from where the optical axis goes through the image sensor to the edge of the image sensor will be exactly half of the height of the image sensor. Now, we were told that in the y direction, the image sensor has 50 degrees angle and 720 pixels. So this here will be 720 divided by 2. And similarly, the distance to the x direction edge of the sensor, so this distance here, will be 1280 divided by 2. So hopefully that makes a bit of sense. I'm going to get rid of some of my annotations here, just simplify them, because this picture will get messy in a second. Yeah, and that just means that if we have some object in the real world that sits exactly on the optical axis, and we want to know where that's going to be positioned, its position on the image sensor is going to be at XY coordinates, or we use UV coordinates when we talk about the image sensor instead of XY. The UV coordinates there are going to be 1280 on 2, which is 640, and 720 on 2, which is, what's that, 360. So, yeah, that tells you the sort of UV coordinates of this point here. So our U-axis is going that way, and our V-axis is going sort of down, because that's how image sensors work. Yeah, that's kind of, actually, sorry, I think I got this a little bit wrong. I think the U-axis should go this way, and the V-axis should go down like that. I know that's technically not a big difference, but just because our U and V origin is going to be right here. But anyway, doesn't really matter that much. Okay, so that's the first thing. We know where our center of our U and V axis is going to be, where the optical center is going to be in terms of its U and V coordinates. And that has a special name. We put U0 and V0 for those coordinates down. And those two numbers are going to be important for us for our intrinsic camera parameters, because the intrinsic camera matrix, or K matrix, looks like this. We have what we call alpha x, we have alpha y, we've got U0, V0, 1, and everything else is 0. So I'm not going to go into too much detail about why that is the case. There's a lot to cover there, but for now, just know that these are the things we're trying to work out. And as you can see, we have already found U0 and V0 just by sort of interpreting that last little statement. Okay, cool. So that's half of the intrinsic camera matrix done. The other half is these two guys over here. Now those are the focal lengths in the X and Y direction. And these are a little bit different in some ways from what you normally think of as the focal length of a lens. Normally when you think about the focal length of a lens, you might think about diagrams that sort of look like this, where, a line that goes parallel to the optical axis goes through the focal length, and a line that goes through the center of the lens is not deviated at all. I should have said focal point here, rather. And this distance from the lens, this is the focal length. We call that f, for obvious reasons. Okay, now, normally that's how we talk about the focal length, but in this case, we just want to sort of calibrate a camera, so we're being a little bit pragmatic. And so we're actually going to calculate the focal length in pixels. Now, how do we do that? Okay, so there's a couple of things we have to remember here. The first thing is that we normally, when we're dealing with cameras on robots, we use a thing called the pinhole approximation. And basically, again, I'm not going to go into the details too much, but basically what the pinhole approximation says is that your image sensor is one focal length away from the lens. So image sensor distance to lens is approximately equal to the focal length. Again, I don't have time here to justify why this is the case. This is something you can sort of, find by looking at pinhole approximation, videos or whatever. But what it means for us is that if we want to find the focal length, we can use a slightly simplified diagram compared to the one we've drawn before. And the diagram we can use is like this. So we have our lens there, even if it's drawn a little bit wonkily. And we've got our optical axis. And here I'm going to sort of take a top-down view. And our image sensor sits, drawn that a little too big. This is our sensor. And this is going to be the width of the sensor. And because the sensor is assumed, according to the pinhole approximation, to be exactly one focal length away from the lens, what that means is that this distance here is one focal length. And crucially, what that also tells us is we can use these angles in a very direct sort of way. Why am I saying that? So the diagram I've drawn here, let's say this is the x-axis. So, this is I guess for our sensor, this will be the u-axis. And we assume that anything that's sort of, in this plane relative to the lens is removed from the optical axis along the x direction. So we've been told that the field of view of our camera is 80 degrees. So that means anything that our lens is going to project onto the sensor is going to be a maximum of 40 degrees away from the optical axis. So to sort of illustrate that, I'm going to draw a line through the lens. Hopefully this will play ball. There we go. Draw another one the other way. I can line those up. Okay, yeah, not bad. Okay, so what this is telling us is that this angle here is 40 degrees because the field of view is the whole sort of cone of light that goes through the lens. That's 80 degrees for the field of view. Okay, now I've explained a lot of stuff, but I don't think I've kind of communicated the sort of bigger picture here. What we're trying to do is calculate the focal length. We don't know what this is at this stage, but we can use the width of the sensor that we've been told, which is 1280 pixels. And we can use the field of view of 80 degrees to calculate what this focal length is going to be in pixels. How do we do that? We just use trigonometry. We know that this angle here is 40 degrees, right? Because it's just the same as this angle here. And we also know that this length here is going to be 1280 on 2, because it's just half the sensor. So if you think back to your high school trig, if we want to calculate the adjacent side to that 40 degree angle using the opposite side and the angle, what are we going to use? We're going to use the tangent, of course. So what we have is that tan of 40 degrees is going to be equal to 1280 on 2 divided by the adjacent angle, or in our case, the focal length. Now, okay, I'll just write focal length here for now. But the specific focal length we're talking about is this alpha x parameter. Because technically, you can have lenses that have a slightly different focal length in the X or Y direction. It may not happen that frequently that we encounter, but it can happen. And the other thing is we are calculating this focal length in pixels, right? But you do sometimes get camera sensors where the pixel size is different in the X and Y direction. And so that's why we have to report this focal length in terms of the number of pixels in the X direction that matches up with the focal length and the number of pixels separately in the Y direction that match up with the focal length. And so that's why we've got two separate calculations here. So we're doing the X calculation now. So we are finding alpha X. And we do that by taking the field of view for X divided by 2, the number of pixels in the X direction divided by 2, and then we'll have the focal length as the denominator in that fraction. So rearranging, we get alpha X equals 1280 divided by 2 on tan 40 degrees. Okay, so just to reiterate, what we're doing here is we're saying tan of the field of view in X divided by 2 equals the width of the sensor divided by 2, also divided by the focal length in X. So this equation you can get directly from that picture. And then when we rearrange, we get that the focal length in X, which is just alpha X, equals the width of sensor divided by 2 divided by tan of the field of view in X divided by 2. And maybe I'll go back to the green calculations here just to do the final calcs. So that's going to be 640 divided by whatever tan 40 is. So grab my calculator. I'm doing this with a real calculator, not on screen. Sorry about that. 640 on tan 40 gives me 762.7 pixels. And I'm just going to put a little X there to indicate that that's in the X direction, because as I said before, you can have different dimensions for pixels. And then finally, we'll do the same for the Y direction, but this time we'll just use the equation. So finding alpha Y, we have we'll put tan field of view in Y on 2 equals width, or maybe I should say height, since we're talking about Y. So height divided by 2, all divided by the focal length in Y, so alpha Y. Rearranging that, we get alpha Y equals, I'm going to sub in the numbers here, so our sensor is 720 pixels high, and we've got 50-degree field of view. So this is going to be 720 on 2 on tan 50 on 2, which is 360 on tan 25. Going to the trusty calculator, 360 on tan 25 gives me 772 pixels in the Y direction. And I'll put 0.0 just to sort of match up with X, but I think normally you would just sort of round to the nearest integer pixel, to be honest. Okay, so that tells us all of the things we need to report K. So our intrinsic parameters are going to be k equals 76. I'm going to round to the nearest pixel now, so I'm going to say 763, and for alpha y we've got 772, so 0, 0, and then u naught was 640 and v naught was 360. 640, 360, 0, 0, 1. And there you have it. The intrinsic parameters are done.